It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappin'? Today, we're going to talk about magnetic field strength and a force acting on a moving charge. In the previous video, we saw that an electron spin causes a magnetic field. So if we take something that we live on, say planet Earth, and we know that Earth is a giant magnet, but the question is, why is it a giant magnet? Well, if we ever took earth science, we know that Earth has an iron core, but the problem with this iron core is that it's too hot to become magnetized. So there has to be another reason for Earth to create a magnetic field. The other thing that hopefully we learned in earth science is that Earth rotates on its axis, and it rotates eastward. So as the Earth is rotating eastward, it's causing the electrons inside the iron to also move in the same direction. And since all these electrons are traveling in the same direction, they're going to have the same magnetic domain, which creates a magnetic field. Now, Earth's magnetic field might be slightly different than what you assumed prior to watching this video or taking this class. But if we were to put a giant bar magnet inside Earth, and we have the North Geographic Pole and the South Geographic Pole, Earth's magnetic field has the South Pole facing in the North Geographic Pole, and the North Magnetic Pole faces in the South Geographic Pole. Now, if you took a compass out and you notice that the red needle points north on a compass, that's because the red needle is the North Magnetic Pole, and it's pointing towards the South Magnetic Pole, which is in the North Geographic Pole. So if we were to draw the magnetic field lines around Earth, we know that they go out of the North Magnetic Pole and into the South Magnetic Pole. And again, notice that the North Magnetic Pole is in the south, and the South Magnetic Pole is in the northern hemisphere. Notice that Earth is spinning eastward and the magnetic poles are north and south, so that the magnetic field is going to be perpendicular to the movement of the electrons or the electron spin. So one thing that we can say is that a moving charged particle since it's charged, it could either be a positive charge or a negative charge, will generate both an electric and a magnetic field. We could also say that the magnetic field is perpendicular to the direction of the charge. To the direction of the charge's movement or spin. As a result of this, imagine if we had a positive charge that's moving to the right of the page, and we place that positive charge in between two magnets. Notice in this case that the positive charge is perpendicular to the magnets. So if the charge is moving to the right, then the magnetic field created by the charge is going to be vertical or perpendicular to its direction. So once that charge reaches inside those two magnets, it'll then be affected by the magnetic field. And this will cause the charge to be deflected in specific directions based on the orientation of the charge as well as the magnetic field. So before we get to the force acting on a moving charge placed in a magnetic field, what I'd like to talk about next is the magnetic field strength. And we'll abbreviate the magnetic field strength with the most obvious letter, capital B. So before we get into the magnetic field strength, let's just do a quick review. We've learned about the gravitational field strength. That's lowercase g is F sub g, the force of gravity, per mass. We also learned about the electric field strength. That was capital E is the electrostatic force per charge. To determine the magnetic field strength acting on a moving charge, we can look at the formula for electric field strength, E equals Fe over Q. But now in this case, we have a charge and it's moving. So we're going to multiply it by the velocity of the charge. And since it could be at an angle or parallel or perpendicular, we're going to include the sine of theta. And that's equal to B, the magnetic field strength. If we look at the picture above, notice that the moving charge is perpendicular to the magnetic field, and in this scenario it's going to experience the greatest amount of magnetic force because the field lines from the charge are also perpendicular to the charge. If the charge were moving parallel to the magnetic field or to the magnets, its magnetic field would be perpendicular to the magnetic field and therefore experience no deflection at all from the two magnets. So when the sine is 90 degrees, we're going to get 1 for sine, which will give us our maximum amount of electric field strength. If the sine is 0 degrees, we'll get 0 when it's parallel to the magnetic field, and it'll experience 0 magnetic field strength. So let's look at the units for the magnetic field strength. We know that the units of force are newtons, the units of charge are coulombs, and the units of velocity are meters per second. Notice inside here, we have a coulomb over a second. That gives us an amp. So the units are going to simplify to as a Newton per amp times meter. And we could condense this into one unit, and we'll call it Tesla, named after Elon Musk. And we could abbreviate Tesla with capital T. We could take this formula and then just get Fe by itself. So we'll get the force acting. We'll get the magnetic force to equal QVB times the sine of theta. So what we're going to do is use what's called the first right-hand rule to determine the direction a charge will move when it's placed inside a magnetic field. We're going to call this the first right-hand rule. We'll be learning 3 of these for the college physics class. So we use the first right-hand rule to determine the direction. Of a moving charge when placed inside a magnetic field. It's important that we use our right hand for this right-hand rule, not our left hand, otherwise we'll get opposite answers. So the first thing for our right-hand rule is we're going to use our thumb to represent the direction of the positive charge. So that means if the charge is moving to the right, we point our thumb to the right. If the charge is moving left, we point our thumb to the left, and so on. The next part of the first right-hand rule is we're going to take our fingers, and our fingers are going to point in the direction of the magnetic field. And remember that the magnetic field goes from the North Pole to the South Pole. And then lastly, for the third right-hand rule, our palm is going to represent the direction of the force acting on the charge. So it represents direction of the force acting on the charge. So if you end up with your palm pointing upwards, that'll mean that the charge is going to move upwards. If your palm ends up pointing to the left, the charge will end up moving, will get deflected to the left. Now just a few things about this. Number one is that if it's a negative charge, so instead of a positive, if we have a negative charge, then we're going to say that the force is opposite direction. As if it were a positive charge. It's opposite direction. As if it were a positive charge. So for instance, if you go through the first right-hand rule and your palm is pointing towards the left, if this were a negative charge, then the charge would be deflected towards the right. So it's just going to be the opposite of what you get for the first right-hand rule for a positive charge. The next thing is that we have 3 dimensions. So we could represent arrows that go up, down, left, and right, but we could also have a charge going in and out of the page. So if a charge is going out of the page, we're going to use a dot, like the tip of an arrowhead. So dot represents out of page. And if the charge is going into the page, we're going to use the fletchings of an arrow, or X, or an X, to represent it's going into the page. So why don't we do a few practice problems together to get an idea of how to use the first right-hand rule. What do you think I do? Teach physics all day? Well, I guess I'll teach some physics after all. So right now we're going to do some practice problems with the first right-hand rule. Just a reminder, our thumb points in the direction of a positive charge. Our fingers point in the direction from the north to the south magnetic pole. And the direction of our palm is going to point towards the force acting on the charge. So if we look at the first example, we have a north pole facing towards the right, south magnetic pole on the opposite side. And we have a positive charge going into the page. That's what the X represents. Since the positive charge is going into the page, we're going to point our thumbs into the page. Our fingers have to go from the north to south pole, so we're going to rotate our fingers so they point from the north to the south pole. If you want to, we can move to the other side to make it easier. And our palm is pointing downwards, therefore the direction of the force acting on the positive charge is downwards. So if my lovely assistant can write, force is directed towards the bottom of the page. Okay, so just to reiterate, since this is our first one, our thumb is going into the wall, our fingers point from the north to the south, and our palm is pointing downwards, therefore the force is downwards. Okay, if you could scroll down to the next one, please. This time we have the north magnetic pole facing upwards, south magnetic pole facing downwards, and our charge is coming out of the page. That's what the tip represents. So our thumb is going to point out of the wall. Our fingers have to point from the north to south pole, so they're going to point upwards. Therefore, our palm is facing towards the left, so the force is going to be directed towards the left of the page. So force is directed towards the left. If you want, we can just draw an arrow going to the left to represent the force. Okay, next one. Now we still have the north on the bottom, south on the top, and the positive charge is going towards the right of the page. So we're going to take our thumb, aim it towards the right of the page. Our fingers are going from the north pole to the south pole, so they're facing upwards. And as we could see, our palm is facing out of the wall. So the charge, or the force acting on the charge, is going to be out of the page. So force is directed out of the page. I'm a herd. All right, and we got one more to go, I believe. Interesting. If you could scroll down a little bit more, please. Let's edit that out. In this example, we've got a negative charge is going to the right of the wall. We'll take that into account in a minute. The magnetic field, we see X's, so the magnetic field is going into the page. So for the time being, let's pretend it's a positive charge. So we'll aim our thumb to the right of the page. The magnetic field is going into the page, so our fingers are going to point inwards. And our palm is pointing upwards. So therefore the charge would be deflected upwards. But since it's a negative charge, it's going to do the opposite of what a positive charge would do. So the negative would be deflected